Good morning and welcome to today's session. Today we are going to discuss the function approximation value prediction. In the last session we have seen how the TD and Monte Carlo methods are unified with the help of TD lambda learning method. In the TD lambda modern view we have discussed how we can view TD lambda in forward view and backward view. In that time we explained how the concept of function approximation is introduced in value updation formula. Okay, in this session we will discuss more on function approximation and also the stochastic gradient descent approach for function approximation updation, and we will see some examples of this function approximation in popular TD method and also Monte Carlo methods. As a continuation of this lecture series, in the next video lesson we will discuss the policy control with approximations. Now we discuss the value updation or value prediction using function approximation. In the coming sessions we will focus on the policy control with function approximations. The important concepts in our discussion are the concept of function approximation methods, the stochastic gradient method, and the working rule of stochastic gradient descent. First of all, let us see what is function approximation. Function approximation in essence is trying to develop a mathematical or empirical function that will help to define value of a state in reinforcement model. For that we will look into these important points. First point is update rule. Update rule is a rule that governs update of a state S to U. For example, suppose a state S has a value 1.3. Using a policy we update it to 1.7. That rule is defined mathematically S to U. That means state S is updated. In TD and Monte Carlo learning we did it with explicit policy pi. We have already discussed how the state values are updated. The state values are updated or evaluated with the help of explicit policies. In the case of temporal difference and Monte Carlo, and even in DP or Markov decision process, we have some explicit policy. Using this policy we evaluate the state values and state action values. But sometimes we don't have such explicit policy, but there is an explicit policy is there, but the agent will have to identify the most suitable policy that will match with the exact or target policy. So in a sense, in functional approximation we did this policy updation with arbitrarily complex and sophisticated methods like neural network weight updation rules to implement the update. That means instead of an explicit policy pi, we make use of output from sophisticated methods like neural network weight updation rules. That means some weight vectors or weight matrix. We calculate or approximate the value of a state S instead of this policy pi. Stochastic gradient descent function approximation. The key points in stochastic gradient descent function approximation are: the basic idea is the vector weight vector W. W is defined as a vector W1, W2, etc. WD transpose. So it is a d-dimensional real numbers. W1, W2, etc. are real numbers. And the approximate value function is denoted by V hat of S comma W. That means the state S will be evaluated with the help of this weight vector, and this weight vector must be a differentiable function of W for all state S in the state space. Why we insist this differentiability? Because the gradient descent make use of the gradient operation. Gradient operation is actually a differentiation. What is the main issue in using this function approximation? The major issue is the function approximator has limited resources and thus limited resolution. That means we cannot find a function approximation that will update all the states in the state space to some exact level. Some function approximation will update some state values well but in some state values this function approximation need not be correct, and so the resolution power of this approximator need not be generalized. That is a major issue. So our aim is to minimize, that means in stochastic gradient descent our aim is to minimize the error in updation. That means st is updated to v pi of st. In this updation of state value we have to ensure that the error in updation is minimum. Then only the actual or the target state value will achieved, or this process will converges to exact value of that state. Okay, so we form a mathematical function. It is denoted by VE bar or value error. This value error is summation of s in state space S mu of s into v pi of s minus v hat of s comma w the whole square. Now look into this function. This is a sum where mu of s is also known as on policy distribution, and v pi of s minus v cap of s comma w the whole square. See, this difference is error. This v pi of s is the actual state value. V cap of s omega is the approximate state value at the state S with the weight vector w. So this is error. So square of error. So this v pi of s minus v hat of s comma w the whole square defines square of the error. Then mu of s is called the on policy distribution. What is the meaning of this on policy distribution? This on policy distribution says how much the square error is important to the state S. If this mu of s is very low, very small, then this square error is very small, or it is negligible to that state S. That means we can explicitly define the importance of square error with the help of on policy distribution. This mu of s is a probability density function, and therefore this mu of s is always positive, and that sum of all mu of s is equal to 1. Once you use this idea here, it is simply an average. The sigma s element of s mu of s into v pi of s minus v hat of s comma omega the whole square or w the whole square defines the expectation. If this mu of s is equal to a uniform distribution, suppose there are s state, n state, this state space S contain n states, capital N, then the probability density function for uniform distribution is 1 by n, and therefore this mu of s becomes 1 by n. So this sigma becomes sigma s over s. This mu of s is 1 by n, v pi of s minus v cap of s comma w the whole square. That becomes the total square error divided by n. Total square error by n means mean square error. That means this v bar of e or value error is the expected square error. This defines the expected square error. When this mu of s is equal to uniform distribution, this becomes the mean square error. So this is a generalization of mean square error. We generalize the concept of mean square error into reinforcement learning. We have already familiar with the concept of mean square error. This mean square error is defined as a cost function. For example, in linear regression models, we try to define mean square error as a loss function. Then we try to minimize the loss square error. In that way, we apply stochastic gradient descent in that model. We do the same in this function approximation. So what is the weight updation formula in stochastic gradient descent? So Wt plus 1 is equal to the current weight minus half times alpha into del of the square error. That is called the stochastic gradient descent. If this minus is replaced by plus, it is called a stochastic gradient ascent formula. Our aim is to minimize this error, so we move in the direction of the minimum error. That is why we put this negative value. And also this half is an adjusting factor. To get a good result for weight updation, I am using this factor 1 by 2. Now Wt plus 1 is equal to Wt minus half into the learning rate alpha into del of v pi of s minus v cap of st comma wt the whole square. Del means partial differential operator. Now we apply the derivative operation. Derivative of square, you just recall the result dy by dx of x square. Derivative of x square, that is 2x. So 2 into this expression in the argument. So we got Wt minus half into alpha into 2 times v pi of s minus v hat of s comma omega, we can specify it st and wt, no problem, into derivative of this expression in the argument. Derivative of this expression means derivative of the first term minus derivative of the second term. V pi of s is constant for a state s, so its derivative 0. So 0 minus del of this expression. Since this omega t contains different components, we have to apply del operator there. So 0 minus, we can exclude 0, so minus into del of this expression, gradient of this expression, del of v cap of s comma xt comma wt. Now this 2 and 2 get cancelled, minus into minus positive, so we got wt plus alpha into v pi of s minus v cap of st comma omega t into del of v cap of st comma omega t. We here insist that we calculate all these v cap, del v cap, etc. at state t. That is why we put t here. Here we do not specify t in this expression. Okay, so the value at the state s can be updated with the help of this weight updation. We are not going to update the value explicitly. We update the state value using this result, so automatically the corresponding state value will be updated. We are trying to correct in weight distribution of the function approximation and not on the policy, because we don't know about the policy in the full swing way. So weight updation using unbiased estimate of v pi of s. Okay, this formula can be executed well if this v pi of s is known in advance. In some situation we don't know what is this v pi of s. That means the policy is not fully known. In such situation we use some expected value for this v pi of s also. That is called the ut. Then what is the quality of ut? Ut should be unbiased estimator for this v pi of s. An estimate is called unbiased estimate, that is ut is called unbiased estimate of this v pi of s if expectation of this ut is equal to v pi of s itself. That means expectation of ut in the state st is equal to v pi of s itself. That means expectation of this ut is v pi of s itself. Then the stochastic gradient formula become, instead of that v pi of s, I am using ut. But remember, this is just an approximation, and therefore this difference or this error will contain some inherent error due to ut. We are trying to calculate error in approximation, but this ut itself is an approximation using unbiased estimator of v pi of s. Hence this ut contains some inherent error, and there is a disadvantage of this inherent error, that is this updation need not be move in the direction of minimum error. There is no guarantee that this difference or this updation formula will move in the minimum error direction. That is one of the disadvantage of using this ut, the unbiased estimate ut, instead of v pi of s. We will see this in more detail. Function approximation for Monte Carlo learning. What happened to this approximation formula when we apply Monte Carlo learning? Suppose we consider some epsilon constant Monte Carlo with the complete return of an episode is gt. So instead of this ut, we just substitute our gt. Look the difference. This is our original formula with ut as an unbiased estimate. When we apply Monte Carlo method, we should apply gt, the epsilon alpha Monte Carlo return, instead of this ut. But note that this gt is an unbiased estimate for v pi of s, that we have already proved in the Monte Carlo learning method. So this is the updation formula. So ut is replaced by gt. Now there is a natural question. If we are using TD function approximation, what will happen to ut? In that case, we will apply the TD target in the place of this ut. We look into that. Before that, we will discuss the pseudo code for Monte Carlo with SGD function approximation. We start with a policy pi. We are going to evaluate this policy to get a stable state values for all the states with some approximation. We input some v cap. This v cap is our approximate value estimate for for all the state S. It is defined as a function from S cross RD to R. We use this S cross RD instead of S to R because this V cap is defined by that weight vector. That weight vector is of dimension D. So it is a cross product, it's a Cartesian product of state values and D-dimensional real line. So V cap from S cross RD to R. We start with the learning parameter alpha. It is greater than 0. Initialize value function weights W to 0 for all components. Then loop for each episode. We have to repeat this for many episodes. Then only we got the stable state values. Generate an episode starting from initial state S0 to terminal state ST with state action reward sequence. We are moving under the policy pi. Loop for each step of episode t equal to 0, 1, 2, etc. t minus 1. We repeat t time steps. T starts from 0 to t minus 1. So there are t steps. The weight updation is W is updated by W plus alpha into GT minus V cap of STW into gradient of V cap of STW. We just use this GT instead of UT in the case of our stochastic gradient formula. Okay, now we move on to the concept of semi-gradient. I told you earlier that if you are using UT instead of V pi of S, it's an approximation. We cannot ensure that we are moving in the minimum error direction. We will expand this idea more. Some more different situations. For example, if the bootstrapping target GTT plus N, that means N step TD, or our DP target, that is expectation of ST, is given by sigma S over S pi of A given us into sigma S dash comma R probability for S dash comma R given S comma A learning discount factor gamma into V cap of S comma omega t in DP. If you are using this bootstrapping measures for return, then it will affect the convergence of SGD because we cannot insist that this particular gradient will move in the minimum error direction. In such cases, SGD itself is called a semi-gradient approach. In that case, SGD is termed as semi-gradient because it is not to the full extent of gradient measures. That is why it is called a semi-gradient approach. So semi-gradient is not a new thing. Semi-gradient is a term that is used to denote a not fully stochastic gradient environment. So SGD function for approximation for TD0. The SGD function approximation is that this is the original formula with an UT, an unbiased estimate for this V pi of S. Then in TD0, this UT is replaced by one step TD target. This formula is like this. Instead of UT, I just substitute RT plus 1 plus gamma into V cap of ST plus 1 omega t minus this V cap of ST comma omega t del of V cap of ST comma omega WT. Omega, in some textbook it is called omega t. In some textbook this weight matrix is denoted by WT. It doesn't matter. So the entire terms in this bracket is called the temporal difference or temporal error. So this is temporal error. So weight updation is in terms of temporal error in the case of TD0. The pseudo code for TD0 SGD function approximation, as in the case of Monte Carlo, we start with any policy that is to be evaluated over states. Then the V cap is from S plus cross RD to R. Here we consider V cap be a state from the terminal state also. There is no restriction. Then V cap of the terminal state is defined as 0. The algorithm parameter, that is step size or learning rate, that should be positive. Initialize value function weights W element of RD arbitrarily. Usually we choose W is equal to 0. If you choose random numbers, there is no problem. Then for each episode, initialize yes. For each step of episode, you choose an action from that state under given policy. Then you just look into the reward and next state corresponding to this action, that is observe R and S dash. Then weight updation is given by weight is updated using the formula W plus alpha into R plus gamma into V cap of next state with the weight vector minus V cap of S with the weight vector into gradient of V cap of S comma W. If the weight updation happens, then we move on to next state. S is updated by S dash. We repeat this procedure for each episode until the end state or the terminal state reached. So the only difference is here we focused on the action from a state to next state and also the immediate return. That immediate return is called the temporal target. We use the temporal target in this updation. Now we move on to linear function approximation. What happened when this V cap of S is a linear function? A linear function means it can be represented in the form of linear combination. That is a key idea. We are already familiar with these linear regression models. If V cap of S is approximated by a linear regression model or linear model, it can be written as W transpose X for this state S. So this can be written as, this is matrix form. In sigma notation, this can be written as sigma I is equal to 1 to D, because capital W is a weight matrix of D dimension. So summation over I from 1 to D, Wi into Xi of S. In this case, the approximate value function is said to be linear, because all the terms in this expression is of power 1 in terms of X, and also this W is also of linear expression. Remember, this is not considered as a polynomial. If it is considered as polynomial, then linear means we focused on the degree of X size. Here this expression is a function of W, so it is a linear in sense of W. Each term in this expansion will contain first degree terms of W. That is very important. So if V cap of S is approximated by a linear function, it is called a linear function approximation. Then the only difference is that del of V cap. When we take del of V cap, that means derivative with respect to W, it gives W of X. When we take derivative with respect to X, with respect to W, not with respect to X, when we take derivative with respect to the weight parameters W, we got a vector in X size, that is an X vector. So the del function becomes the vector Xi. If we consider Xi's are features, this gradient of V cap leads to the vector of features, or simply feature vector. So that is the advantage of using linear function approximation. I repeat, in the case of linear function approximation, del of V cap leads to our feature vector. So we use these feature vector values in weight updation. That is the only difference in applying linear function approximation in the place of our general V cap of S comma omega W. So what is the difference in weight update in linear function approximation? So this is our usual formula for weight updation. In the case of stochastic gradient descent, Wt plus 1 is defined as Wt plus learning rate into Ut, an unbiased estimate for V pi of S, minus V cap of St comma Wt into del of V cap of S. In the place of del of V cap of S, we get X of St. X of St is called the feature vector. So weight updation is happened in terms of this X of St. Then what is X of St? That is our feature vector. So SGD TD0 approximation, the difference is that this U of t will be updated by our temporal target, and X of xt is the feature vector. So thus U of t is replaced by RT plus 1 plus gamma into V cap of St plus 1 Wt minus V cap of St comma Wt into del of, or gradient of V cap of St comma Wt. Now replace this del of V cap of St comma Wt by our target vector X of t, and we can update this V cap of St plus 1 comma Wt in terms of our X. So V cap of St plus 1 Wt can be replaced by omega transpose X, or here it is W transpose X. So Wt transpose Xt plus 1. Why we use Xt plus 1? Here we are using Xt plus 1. So next state value of X is used, minus here V cap of St comma Wt. Instead of that, we use W transpose T Xt into gradient of this omega transpose Xt gives Xt. Then we apply some matrix manipulation. This omega t is defined for all t, that defined capital omega t, and this omega t plus 1 become capital omega t plus 1. This omega t plus alpha into RT plus 1 into this xt. We have to multiply this entire expression by xt. minus, I am taking this xt common, considering these both terms. So xt into, so we got here, I take minus also outside. So I take minus xt outside. So this term become negative, this term become positive. So I take xt outside. So omega transpose txt minus gamma into omega t transpose xt plus 1. Then I use a matrix manipulation, that is, I take omega t outside, and so this expression changes to the transpose form. So xt minus gamma into xt plus 1 transpose. This is simply a matrix manipulation. My aim is to express this weight updation in terms of difference of these x values, because it has some advantages. So weight updation formula becomes wt plus alpha into rt plus 1 capital XT minus capital XT into XT minus gamma into XT plus 1 transpose omega t. So new weight update is in terms of previous weight value, or the current new weight updation, that is wt plus 1 is equal to in terms of wt and the difference of x values. This difference of x values is called spatial difference or sparse difference, because xt into xt minus gamma into xt plus 1 transpose is called the sparse difference. The sparse difference is a minor version of covariance matrix. So this is like a covariance, but in the case of covariance formula there is a division by term, but there is no division term here. So it is considered as a sparse measure. So this sparse measure of x take major role in weight updation. Or in a single sentence we can say that in the linear function approximation TD0, the weight update happens in terms of sparse difference of feature values, sparse difference of or sparse measures of difference values. The difference of which values? Difference of these feature values. Okay, this is all about the linear function approximation. So in this lesson we start with the concept of function approximation. Instead of exact value of states, we make use of some function approximation. Okay, this function approximation help us to define the state value approximately. Then we try to minimize this approximation error. For that we will use stochastic gradient descent method. So this stochastic gradient descent method will be generalized to different contexts, for example Monte Carlo, TD and TD0, etc. Then we will see what is the linear function approximation. Instead of VCAP of S comma W, we use a linear approximation, that is omega transpose x. Then what happens the stochastic gradient if this approximation function or function approximation is linear? Then the weight update becomes a sparse measure in terms of current weight. The new weight wt plus 1 is in terms of a sparse difference or sparse measure of the feature vectors and wt, the current weight update. So this is all about our basic concept of function approximation. There is a natural question why we are using function approximation. One answer is that we don't know the exact value of a state at a particular instant. Then how we will start with our learning algorithm? So this approximation help you. But remember, this function approximation may be a linear function, a polynomial function, a Fourier transform, whatever it is. It may be a weight vector or weight matrix from a neural network. So in that instance, if we are using machine learning approach, the output from a neural network is given to the function evaluation. The output is the full information of the state. So the full information from a neural network is transformed into a reinforcement learning environment. So what happened? The agent will start learning from the output of a neural network. Then what is really a neural network will do? A neural network, an artificial neural network, simply imitate human neural network. So our intelligence, how we identify things, how we classify things, all these can be imitated by this artificial neural network. So the human thinking will be replaced with the help of the artificial neural network. So what human think, what human perceive, all these ideas are transmitted to this reinforcement learning environment through this artificial neural network weight matrix. Now the agent is at a state to get the full information of a context. Now we define all the rules, learning rules for this agent based on this neural network weight. Then what happened? This agent's movement is almost accurate. That will minimize the error and maximize the return. So this approach of introducing function approximation with the help of neural network will do connecting human thinking into human action. So human thinking part is handled by our machine learning algorithm, especially neural network algorithm. Then I connect into the reinforcement learning environment. This execution or the action part will facilitate it. So a well-defined neural network function approximation will help us to design the brain of a artificial agent. So this is the base of intelligent machine. An intelligent machine will get intelligent information, and he will make use of this intelligent information and act accordingly. So in a single sentence, a reinforcement learning with function approximation from neural network will facilitate a beautiful situation. What is that situation? That situation provides a software for a robot. It will act as a software for a robot. Once you have all the hardware for the robot, this neural network plus reinforcement learning will support a very good contextual software for that robot or bot or whatever it is. So the reinforcement learning will act as a topping for our machine learning algorithms. It will come into the implementation level. Now the software is ready to implement in a robot. So intelligent machine can be devised with the help of connecting the neural network function approximation into reinforcement learning. So we will see more about this idea, especially the policy control, in next session. Now we focused only on the value prediction. Naturally there is policy control, generalized policy control for this function approximation. So we will discuss this in coming sessions. Okay, thank you.